Hello, and thank you for taking a look at my presentation today. My name is Nephi Stanford, and for my ME 423 semester project, I decided to analyze the thermoelectric cooler. A quick introduction to what a thermoelectric cooler is. You've got two heat sinks with a couple semiconductors sandwiched between them, and the two semiconductors have different charges on them when they're energized, and that difference in electrostatic potential also creates a temperature gradient through what's called the Peltier effect. So if you take a bunch of these semiconductors, put them in series between two plates, there you have it. Now the cooler that we're looking at is this Coleman cooler that my wife and I purchased. These coolers are often used for families and truckers just to keep the food cool. So a little background on that. We went road tripping through the USA last summer, ran into a few problems with our cooler. One, the cooling was sporadic. Another, wouldn't stay cold for very long and it was bulky. So we went to go sightseeing or went shopping. Your food would often heat up and then it would take a while for it to cool back down, so you're always chasing it. So the three questions I really want to answer with this project were: one, the claim that 22 degrees difference between the inside and outside the cooler, is that consistent through a different temperature range in the car? And can the cooler effectively remove enough heat to provide enough cooling within a short amount of time in the car? The third question was, can the cooler keep the food cool for at least an hour while you're off shopping, visiting the sites? So in order to find the first question, I took three different temperature measurements throughout my temperature range. And the one was the outside ambient temperature, and then the heat sinks on the hot and cold side. I didn't bother with the temperature inside the cooler, simply because when you're going up, the heatsink actually ends up heating the food and it ends up cooling it on the way back down. But with that being said, just trying to figure out heat transfer coefficients and everything with the food, it was very challenging. So the temperature I could control was the outside temperature, and so we'll go back to T1 and T2 for our calculations. Moving forward, this is how the hardware looked when it was hooked up. It was measuring the temperature right at the base of the fin on top of the actual base itself. So here's the thermometer making the measurements. A couple interesting things: I had a floor fan mixing up the air that I thought would make the whole room the same temperature, but it ended up I couldn't keep the room hot enough because the cement and the toilet in the corner were just sucking all the heat that I was putting into the room. And the heat sinks themselves are very sporadic, so I had to take an average value when I tabulated it. Now, if you're measuring the heat sinks, they should have a wider spread than what it's claimed, because your heat sinks have to pull heat and move it out, versus just the inside and outside temperatures. So with that being said, here's the measurement of the hot and the cold. Now if that temperature difference was the same throughout all my measurements, we'd see parallel lines, but here you can see it kind of spreading. Another graphic here with the bars really shows it well in great detail. The measured, in most cases, in all the cases in fact, never reached what they're claiming. And this is, remember, on the heatsink, so it should be greater than what's claimed, but it's not. And in fact, the percent error between the two was an average of 30%. On top of that, the coldest the heatsink ever got when we measured at a room temperature of 15.6 degrees was around 6 degrees Celsius. And for refrigerators to keep your food out of the danger zone, they need to be around 4 degrees Celsius. So it's kind of a flop there. The next question we had, reasonable cooling time. A couple assumptions here. The velocity crossing the fins is the same as the velocity going out the center of that shroud. And the heat sinks weren't totally symmetrical, so we had to average out some of the widths, the spacing, and the height. Here is my process of thinking with my calculations, and for my example that I have written out, I took it at a fluid temperature of 275 Kelvin. So with your properties, you find your Reynolds number, which both cases of the hot and cold, they're both laminar. Then you find the appropriate Nusselt correlation. The correlation I chose was constant heat flux that was laminar. With that Nusselt correlation, you get your heat transfer coefficient, and then you can then find your resistance for the fins. Now with this, we had to do a flat plate estimation, and that's what we put into the Nusselt correlation to find our R total. So here's it being worked out. The R cold I thought would be less than, more than the R hot, because it was a smaller heat sink, wasn't the case, and I think that was mostly based on the velocities. Then to see a reasonable cooling time, rather than trying to figure out heat transfer coefficients with shapes and everything inside and velocities, I just took the bulk mass of what I wanted to cool by its heat capacity and the desired temperature change. So it was a 12 pack of soda, considering it water at room temperature, and I wanted to change it a difference of 15 degrees. Now, with that being said, in order to find how long it takes, you need to have a temperature gradient within the cooler. So I got temperature gradient all the way up to 4.5 degrees Celsius, and it still took me 6 hours to drop the pop cans down 15 degrees. So that totally throws out the initial claim of the 20 degrees spread, because we just lost another 5 degrees in order to achieve a decent cooling time. So this is another whack out here. The cooling time isn't matching up as well as the temperature spreads. So how about the heating time with no power? In order to find that what temperature I should set the box at, I ran a couple tests to see what does sunlight do to the interior car compared to the outside temperature. So in heating and cooling the car a couple times, I found that the interior will be about 10 degrees Celsius warmer on a sunny day, and that's on a sunny day that's 17 degrees Celsius outside. And this, of course, done the Chrysler Sebring that we were working with before. So taking that, I said, okay, we got a warm day that's about 30 degrees. It'll probably be car interior 40 degrees Celsius. So I kept my soda cans in a room at 40 degrees Celsius, and I wanted to see what the temperature change would be in 30 minutes. So I found, you can see that wire is going to the middle of the cans. Inside temperatures change of 1.3 degrees Celsius. I gave myself a safety factor by timesing it by 2, because the outside ring of food might be quite a bit warmer than the inside. So in 1.5 hours, you have a potential 7.8 degrees Celsius rise. So the conclusion of that is, yeah, it was kind of a fail. The temperature gradient didn't work out, the cooling time didn't work out, and the heating time is sort of reasonable, but an hour and a half, you lost half of the original temperature difference. So, 3 hours out to movie or whatever else, you're totally. Another couple considerations is sporadic behavior. Plugging it into the splitter versus directly, it made an issue. And you make sure you have at least 6 amps if you have an adapter going into the house. Thank you for taking a look at my project, and really appreciate your time. Here's a couple of links to the pictures that were included, and that's all I have for you. Thanks.